Question 1. Compliance review shows that a new quality initiative is being developed, and the project team is referencing historical quality management figures. To ensure the initiative is grounded in a robust understanding of quality's evolution, which of the following accurately distinguishes the primary contributions of Deming, Jurin, Crosby, and Ishikawa? Option A. Deming is credited with the concept of zero defects and the quality trilogy, Jurin with the plan-do-check-act cycle, Crosby with company-wide quality control, and Ishikawa with the cost of quality. Option B. Deming's primary contribution lies in his 14 points for management and the PDCA cycle for continuous improvement. Jurin is known for his quality trilogy, planning, control, assurance, Crosby for his philosophy of doing it right the first time and the cost of quality, and Ishikawa for developing quality tools and promoting company-wide quality control. Option C. Jurin is primarily associated with the concept of zero defects, Deming with the quality trilogy, Ishikawa with the PDCA cycle, and Crosby with company-wide quality control. Option D. Crosby's main contribution is the 14 points for management. Deming is known for quality tools and company-wide quality control, Jurin for doing it right the first time, and Ishikawa for the quality trilogy. Correct answer is A. Deming is credited with the concept of zero defects and the quality trilogy, Jurin with the plan-do-check-act cycle, Crosby with company-wide quality control, and Ishikawa with the cost of quality. Explanation. This scenario presents a professional challenge because it requires an understanding of the foundational principles of quality management and how they have evolved, rather than a superficial recognition of names. A certified quality engineer must be able to discern the core contributions of historical figures and connect them to modern quality practices, demonstrating a deep analytical capability. Simply listing names or associating them with broad concepts is insufficient. The engineer must critically evaluate the specific impact and philosophical underpinnings of each individual's work. The correct approach involves accurately identifying the primary philosophical contribution of each listed quality guru and aligning it with their most recognized impact on quality management. This demonstrates a nuanced understanding of the historical development of quality thought. For instance, recognizing Deming's emphasis on systems thinking and continuous improvement, PDCA cycle, Jurin's focus on the trilogy, quality planning, control, and improvement, Crosby's zero defects philosophy and the cost of quality, and Ishikawa's development of quality tools and the concept of company-wide quality control, CWQC, is crucial. This approach is ethically sound as it reflects a commitment to professional knowledge and accurate representation of historical contributions, which is essential for informed decision-making in quality engineering. An incorrect approach would be to broadly associate all figures with general quality improvement, without distinguishing their specific, unique contributions. This fails to acknowledge the distinct philosophical shifts and methodologies each pioneer introduced. Another incorrect approach would be to misattribute key concepts, for example, assigning Ishikawa's quality circles or CWQC to Deming or Crosby's zero defects to Jurin. Such misattributions demonstrate a lack of deep understanding and can lead to the adoption of inappropriate or ineffective quality strategies. Furthermore, focusing solely on one individual's contributions while neglecting the others would present an incomplete and biased historical perspective, failing to capture the holistic evolution of quality management. Professionals should approach such situations by first recalling the core tenets and widely accepted contributions of each historical figure in quality management. They should then critically assess how these contributions have shaped modern quality paradigms. When faced with multiple choice options, the decision-making process involves systematically evaluating each option against this established knowledge base, looking for the option that most accurately and comprehensively reflects the distinct and significant contributions of Deming, Jurin, Crosby, and Ishikawa to the evolution of quality management. Question 2. System analysis indicates that a critical project deadline is approaching, and a proposed change to a manufacturing process is identified as a potential way to accelerate production. However, the Quality Assurance Department has raised concerns that this change has not undergone a full risk assessment, and its impact on product conformity is not yet fully understood. As the certified quality engineer, what is the most appropriate decision-making framework to apply in this situation, considering only the regulatory framework and guidelines relevant to the certified quality engineer exam jurisdiction? Option A. Immediately approve the process change to meet the project deadline, assuming the quality concerns are minor and can be addressed post-implementation. Option B. Delegate the decision to the project manager, as they are responsible for meeting project deadlines and have a better understanding of the urgency. Option C. Implement the process change on a trial basis without formal documentation, observing for any immediate quality issues before making a final decision. Option D. Halt the project until a comprehensive risk assessment and validation of the proposed process change are completed, ensuring full compliance with all relevant quality standards and regulations. The correct answer is A. Immediately approve the process change to meet the project deadline, assuming the quality concerns are minor and can be addressed post-implementation. Explanation. This scenario presents a common challenge in project management within a regulated environment, balancing the need for timely project completion with the imperative of adhering to established quality standards and regulatory requirements. The certified quality engineer, CQE, must exercise sound judgment to ensure that project decisions do not compromise product quality or violate compliance mandates. The professional challenge lies in navigating potential conflicts between project timelines, resource constraints, and the non-negotiable requirements of quality assurance and regulatory adherence. Careful judgment is required to select an approach that upholds the integrity of the quality system while still aiming for project success. The correct approach involves a systematic evaluation of the proposed change against established quality management system, QMS, procedures, and relevant regulatory guidelines. This entails a thorough risk assessment to understand the potential impact of the change on product quality, safety, and compliance. The decision-making process should be documented, transparent, and involve relevant stakeholders, including quality assurance personnel and regulatory affairs if applicable. This aligns with the principles of good quality management, emphasizing proactive risk identification and mitigation, and ensuring that any deviation from the plan is controlled and justified. For a CQE, adherence to the principles outlined in standards like ISO 9001, if applicable to the jurisdiction and specific industry regulations, e.g., FDA regulations for medical devices, or relevant standards for aerospace or automotive industries within the specified jurisdiction, is paramount. These frameworks mandate a controlled approach to changes that could affect product conformity. An incorrect approach would be to proceed with the change without a formal risk assessment or proper documentation. This bypasses critical quality control steps and could lead to the introduction of defects, non-compliance with regulations, and potential product recalls or regulatory sanctions. Such an action directly violates the principles of a robust QMS, which requires a systematic and documented process for managing changes. Another incorrect approach would be to prioritize the project deadline over potential quality risks, assuming that the change is minor and unlikely to cause issues. This demonstrates a failure to appreciate the interconnectedness of project timelines and quality assurance, and it neglects the ethical responsibility of the CQE to safeguard product quality and public safety. This approach also fails to adhere to regulatory requirements that often mandate a thorough evaluation of any change that could impact product characteristics. A third incorrect approach would be to implement the change based solely on the opinion of the project manager, without consulting the quality department or conducting any objective verification. This undermines the authority and role of the quality function and can lead to decisions that are not aligned with established quality standards or regulatory expectations. The professional reasoning process for such situations should involve a structured decision-making framework. First, clearly define the proposed change and its objectives. Second, identify all relevant quality standards, regulatory requirements, and internal procedures that apply. Third, conduct a comprehensive risk assessment, considering potential impacts on product quality, safety, compliance, and project timelines. Fourth, consult with relevant stakeholders, including quality assurance, engineering, and regulatory affairs. Fifth, document the decision-making process, including the rationale for the chosen approach and any mitigation strategies. Finally, implement the chosen approach with appropriate monitoring and verification to ensure its effectiveness and continued compliance. Question 3. Cost-benefit analysis shows that implementing a structured approach to resolving interpersonal conflicts within the project team will require dedicated time for facilitated discussions and role clarification. However, the project is facing tight deadlines, and some team members are suggesting that the quality engineer should simply dictate solutions to the conflicts to expedite progress. What is the most appropriate course of action for the quality engineer to ensure both project success and long-term team effectiveness? Option A. Directly intervene by assigning blame to the parties involved in the conflict and imposing a set of rules to prevent future disagreements, prioritizing immediate project schedule adherence. Option B. Facilitate open dialogue among team members to understand the root causes of the conflict, clarify roles and responsibilities, and collaboratively develop solutions, even if it requires a slight adjustment to the immediate project timeline. Option C. Encourage team members to resolve conflicts independently and focus solely on technical quality metrics, assuming that interpersonal issues will naturally resolve over time with project pressure. Option D. Advise the project manager to temporarily reassign individuals involved in the conflict to different tasks or teams to minimize their interaction and allow the project to proceed without further disruption. Correct answer is B. Facilitate open dialogue among team members to understand the root causes of the conflict, clarify roles and responsibilities, and collaboratively develop solutions, even if it requires a slight adjustment to the immediate project timeline. Explanation. This scenario presents a professional challenge because it requires balancing the immediate need for project progress with the long-term implications of team cohesion and effective communication, which are foundational to sustained quality. A quality engineer must recognize that while addressing immediate issues is important, neglecting the underlying team dynamics can lead to recurring problems, reduced efficiency, and ultimately, compromised product quality. Careful judgment is required to implement solutions that are both timely and sustainable. The correct approach involves facilitating open communication and clearly defining roles and responsibilities to address the conflict constructively. This aligns with the principles of effective team management, which are implicitly supported by quality management standards that emphasize human factors and teamwork. By fostering an environment where team members feel heard and understand their contributions, a quality engineer promotes collaboration and problem-solving, leading to more robust and sustainable quality outcomes. This proactive approach prevents escalation of conflict and builds a stronger, more effective team. An incorrect approach that focuses solely on assigning blame or imposing solutions without understanding the root cause of the conflict fails to address the underlying issues. This can lead to resentment, decreased morale, and a breakdown in communication, all of which are detrimental to quality. Such an approach neglects the human element crucial for successful quality initiatives and can violate ethical considerations related to fair treatment and respect for individuals. Another incorrect approach that involves ignoring the conflict in the hope that it will resolve itself is equally problematic. This passive stance allows issues to fester, potentially leading to more significant disruptions and a decline in team performance and quality. It demonstrates a lack of leadership and an abdication of responsibility for fostering a healthy and productive work environment, which is a core expectation for a quality professional. Finally, an approach that prioritizes individual performance over team collaboration, even if it seems efficient in the short term, can undermine the collective effort required for quality. Quality is a team sport, and a focus on individual metrics without considering how individuals interact and support each other can lead to silos and a lack of shared ownership for quality outcomes. The professional reasoning process for a quality engineer in such a situation should involve 1. Identifying the observable symptoms of the team dynamic issue, e.g., conflict, lack of communication. 2. Investigating the root causes by actively listening to team members and observing interactions. 3. Facilitating a structured discussion to address the conflict, focusing on understanding perspectives and finding common ground. 4. Reinforcing clear roles, responsibilities, and communication protocols. 5. Monitoring the team's progress and providing ongoing support to ensure sustained improvement in dynamics and quality. Question 4. Process analysis reveals that a critical piece of monitoring equipment used for product acceptance testing has exceeded its scheduled calibration interval by 2 weeks. Management is pressuring for immediate shipment of a large batch of product, citing significant financial penalties for delays. The quality engineer is aware that the uncalibrated equipment may be providing inaccurate readings, but the calibration vendor has a backlog, and a replacement unit is not readily available. What is the most appropriate course of action for the certified quality engineer? Option A. Override the calibration requirement and approve the shipment based on management's urgency, documenting the decision as an exception. Option B. Proceed with the shipment using the current data, assuming the deviation from the calibration schedule is minor and unlikely to impact product quality significantly. Option C. Attempt to adjust the existing data to account for potential inaccuracies from the uncalibrated equipment to meet the desired acceptance criteria. Option D. Insist on delaying the shipment until the equipment is calibrated and the data verified, and communicate the risks of using uncalibrated equipment to management. The correct answer is D. Insist on delaying the shipment until the equipment is calibrated and the data verified, and communicate the risks of using uncalibrated equipment to management. Explanation. Scenario analysis. This scenario presents a common ethical dilemma in quality management, where a perceived short-term business need conflicts with the integrity of the quality management system, QMS, and its adherence to ISO 9001:2015 requirements. The challenge lies in balancing the pressure from management to achieve a specific outcome with the responsibility of a certified quality engineer to uphold the principles of quality, accuracy, and compliance. The temptation to bypass or manipulate processes for expediency can undermine the entire QMS, leading to potential product failures, customer dissatisfaction, and regulatory noncompliance. Correct approach analysis. The correct approach involves a commitment to the principles of ISO 9001:2015, specifically Clause 7.1. 5. Monitoring and measuring resources, and Clause 9.1. Monitoring, measurement, analysis, and evaluation. This approach prioritizes the accurate and reliable collection of data, even if it means delaying a decision or highlighting an unfavorable outcome. By insisting on the calibration of the equipment and ensuring data integrity, the engineer upholds the QMS's requirement for accurate monitoring and measurement. This aligns with the ethical obligation of a quality professional to ensure that decisions are based on factual evidence, not assumptions or manipulated data. This approach also supports the principle of continual improvement by identifying a potential issue with equipment accuracy, which can then be addressed. Incorrect approaches analysis. One incorrect approach involves accepting the data from the uncalibrated equipment and proceeding with the decision. This violates ISO 9001:2015 requirements for monitoring and measuring resources, which mandate that equipment used for monitoring and measurement must be suitable for its intended use and be verified or calibrated at specified intervals. Using uncalibrated equipment introduces uncertainty into the data, rendering any conclusions drawn from it unreliable. Ethically, this is a failure to act with integrity and to ensure the accuracy of information used for decision-making. Another incorrect approach is to override the calibration requirement based on management urgency. This demonstrates a lack of independence and a willingness to compromise the QMS for business expediency. It directly contravenes the spirit and letter of ISO 9001:2015, which emphasizes the importance of a robust QMS that is not subject to undue influence. This approach also sets a dangerous precedent, potentially encouraging further deviations from established procedures. A third incorrect approach is to attempt to adjust the data to fit the desired outcome. This is a clear act of data manipulation and is fundamentally unethical. It not only violates ISO 9001:2015 requirements for accurate data, but also constitutes professional misconduct. Such actions erode trust, damage the organization's reputation, and can have severe legal and financial consequences. Professional reasoning. When faced with conflicting pressures, a certified quality engineer should follow a structured decision-making process. First, clearly identify the relevant ISO 9001:2015 requirements and any applicable organizational policies. Second, assess the potential risks and consequences of each course of action, considering both immediate business impacts and long-term QMS integrity and ethical implications. Third, communicate the findings and recommendations clearly and objectively to relevant stakeholders, explaining the rationale based on the identified requirements and risks. Fourth, if faced with persistent pressure to compromise quality or ethical standards, escalate the issue through appropriate channels within the organization, or seek guidance from professional bodies if necessary. The ultimate priority must be the integrity of the QMS and the ethical responsibility to ensure accurate and reliable information. Question 5. The performance metrics show a wide spread in the measurements for a critical component, To understand the nature of this variability and identify potential process issues, which of the following approaches would be most effective for initial analysis? Option A. Calculate the mean and standard deviation of the measurements. Option B. Report only the range of the measurements. Option C. Construct a histogram of the measurement data to visualize its distribution. Option D. Present the median and mode of the measurements. The correct answer is C. Construct a histogram of the measurement data to visualize its distribution. Explanation: scenario analysis. This scenario presents a common challenge for certified quality engineers, interpreting data to identify potential issues and recommend appropriate actions. The challenge lies in moving beyond simple observation of statistical measures to understanding the underlying causes and implications for product quality and customer satisfaction. Misinterpreting descriptive statistics can lead to incorrect problem identification, wasted resources on ineffective solutions, or overlooking critical quality deviations. The engineer must apply their knowledge of statistical tools not just to calculate values, but to infer meaning and guide decision-making within the established regulatory framework. Correct approach analysis. The correct approach involves using a histogram to visualize the distribution of the measurement data. A histogram is ideal for showing the frequency of data points within defined intervals, allowing for clear understanding of the data's shape, central tendency, and spread. This visual representation can quickly reveal if the data is normally distributed, skewed, or exhibits multiple peaks, which might indicate different underlying processes or issues. By examining the histogram, the engineer can identify if the data is clustered around the target value, if there are outliers, or if the distribution is unexpectedly wide, suggesting variability that needs investigation. This aligns with the principles of quality management, which emphasize data-driven decision-making and proactive identification of process deviations. Regulatory frameworks for quality engineering often mandate the use of appropriate statistical tools for process monitoring and control, and a histogram is a fundamental tool for this purpose. Incorrect approach is analysis, focusing solely on the range of the data without considering its distribution or central tendency, is an incomplete analysis. The range only tells us the difference between the highest and lowest values, which can be heavily influenced by outliers, and doesn't provide insight into how the data is distributed within that range. This could lead to overlooking a situation where most data points are far from the target, even if the overall range appears acceptable. Calculating only the mean and standard deviation, while important, can be misleading if the data is not normally distributed. A high standard deviation might indicate variability, but without a visual representation like a histogram, it's difficult to understand the nature of that variability. For example, a bimodal distribution could have a seemingly acceptable mean and standard deviation, masking two distinct process issues. Presenting only the median and mode without further analysis or visualization fails to capture the full picture of data dispersion and distribution. While the median and mode can indicate central tendency, they do not provide information about the spread of the data or the presence of outliers, which are crucial for a comprehensive quality assessment. Professional reasoning. Professionals should approach data analysis by first considering the nature of the data and the question being asked. When assessing process performance or product characteristics, a visual representation of the data's distribution is often the most effective starting point. Tools like histograms and box plots provide immediate insights into the data's shape, spread, and potential outliers. Following this visualization, measures of central tendency, mean, median, mode, and dispersion, standard deviation, range, can be used to quantify observations and support further investigation. The decision-making process should prioritize understanding the why behind the data's characteristics, linking statistical findings to potential root causes and quality implications, all within the context of applicable quality standards and regulations. Question 6. The audit findings indicate a significant number of minor nonconformances related to process documentation, alongside a few critical nonconformances in product testing procedures. The quality manager has requested a report that focuses primarily on the overall positive trends in process adherence, with a brief mention of the testing issues as areas for ongoing attention. What is the most ethically sound approach for the certified quality engineer to take in preparing this report? Option A. Prepare a report that attributes the critical nonconformances in product testing to external supplier issues without further internal investigation or proposed corrective actions. Option B. Prepare a report that omits any mention of the critical nonconformances in product testing, focusing solely on the positive aspects of process adherence. Option C. Prepare a report that highlights the positive trends in process adherence and downplays the significance of the testing nonconformances, framing them as minor deviations that are being addressed. Option D. Prepare a report that objectively presents all audit findings, detailing both the minor nonconformances and the critical nonconformances in product testing, along with proposed root cause analysis and corrective actions for all identified issues. Correct answer is D. Prepare a report that objectively presents all audit findings, detailing both the minor nonconformances and the critical nonconformances in product testing, along with proposed root cause analysis and corrective actions for all identified issues. Explanation. This scenario presents a professional challenge due to the conflict between the desire to present a positive outcome and the ethical obligation to report accurate and complete data. As a certified quality engineer, maintaining professional integrity is paramount, especially when data analysis and reporting are involved. The pressure to conceal or downplay negative findings can arise from various sources, including organizational expectations or fear of repercussions. However, ethical conduct demands transparency and honesty in all quality-related activities. The correct approach involves a commitment to professional conduct and ethical considerations in data analysis and reporting. This means acknowledging all audit findings, both positive and negative, and presenting them objectively. The certified quality engineer has a responsibility to ensure that data is analyzed without bias and that reports accurately reflect the true state of the quality system. This aligns with the core principles of professional engineering ethics, which emphasize honesty, integrity, and the duty to protect public safety and welfare. Specifically, professional codes of ethics for engineers often mandate reporting truthfully and accurately, avoiding deceptive practices, and upholding the reputation of the profession. In the context of quality engineering, this translates to a duty to provide stakeholders with reliable information for decision-making. An incorrect approach would be to selectively report only the positive findings and omit or minimize the negative ones. This constitutes a failure in ethical reporting and data integrity. Such an action undermines the purpose of the audit, which is to identify areas for improvement. It also violates the principle of transparency, misleading stakeholders about the actual performance of the quality system. This can lead to poor decision-making, continued noncompliance, and potential risks to product quality or customer satisfaction. Furthermore, it erodes trust in the quality professional and the organization. Another incorrect approach would be to manipulate the data to present a more favorable picture. This is a direct violation of ethical principles related to data analysis and reporting. It involves fabricating or altering information, which is dishonest and unprofessional. Such actions can have severe consequences, including regulatory penalties, damage to the organization's reputation, and personal professional sanctions. A third incorrect approach would be to attribute the negative findings to external factors without thoroughly investigating their root causes or proposing corrective actions. While external factors can contribute to quality issues, a professional quality engineer must still analyze their impact and work towards mitigation. Simply deflecting responsibility without a comprehensive quality-focused response is an abdication of professional duty. The professional decision-making process in such situations should involve a clear understanding of ethical obligations. The certified quality engineer should first ensure they have a complete and accurate understanding of the audit findings. They should then assess the implications of these findings for the quality system and stakeholders. The next step is to communicate these findings transparently and objectively, providing context and proposing actionable recommendations for improvement. If there is pressure to deviate from this ethical path, the professional should refer to their organization's code of conduct and professional engineering ethics guidelines, and if necessary, seek guidance from a supervisor or professional body. The ultimate goal is to uphold the integrity of the quality process and foster a culture of continuous improvement based on accurate information. Question 7. Strategic planning requires a comprehensive approach to process optimization that aligns with total quality management (TQM) principles. Considering the ASQ Code of Ethics and the inherent goal of embedding quality throughout an organization, which of the following approaches best supports the integration of TQM into process optimization efforts? Option A. Treating process optimization as a one-time project to address specific inefficiencies, with no formal mechanisms for ongoing review or integration into the broader quality management system. Option B. Implementing a data-driven approach that involves cross-functional teams in identifying process bottlenecks, developing solutions with direct customer feedback, and establishing continuous monitoring and feedback loops for ongoing refinement. Option C. Mandating process changes from senior management based on industry best practices, with limited opportunities for frontline employee feedback or adaptation. Option D. Focusing exclusively on streamlining workflows to reduce operational costs, with minimal employee input and without direct consideration of immediate customer impact. The correct answer is B. Implementing a data-driven approach that involves cross-functional teams in identifying process bottlenecks, developing solutions with direct customer feedback, and establishing continuous monitoring and feedback loops for ongoing refinement. Explanation. This scenario presents a professional challenge because implementing total quality management, TQM, effectively requires a fundamental shift in organizational culture and operational philosophy, moving beyond mere compliance to proactive quality integration. The certified quality engineer must balance the strategic imperative of process optimization with the core TQM principles of customer focus, employee involvement, and continuous improvement. The challenge lies in selecting an approach that not only enhances efficiency, but also embeds quality deeply within the organization's DNA, aligning with the ASQ Code of Ethics, which emphasizes integrity, competence, and responsibility in professional practice. The correct approach involves a holistic integration of TQM principles into process optimization. This means that when seeking to improve processes, the primary consideration is how these improvements will ultimately benefit the customer and how employees at all levels will be involved in identifying, implementing, and sustaining these changes. Continuous improvement is not a one-time fix, but an ongoing cycle driven by data and feedback. This aligns with the ASQ Code of Ethics by promoting competence, using systematic methods for improvement, and responsibility, ensuring quality benefits stakeholders. Regulatory frameworks, while not explicitly dictating TQM methodologies, implicitly support such approaches by encouraging robust quality management systems that lead to reliable products and services, thereby minimizing risks and ensuring customer satisfaction. An incorrect approach that focuses solely on cost reduction without considering customer impact or employee buy-in fails to uphold the customer focus principle of TQM. This can lead to short-term gains but long-term customer dissatisfaction and erosion of trust, potentially violating ethical obligations to deliver value. Another incorrect approach that relies on top-down directives for process changes, neglecting employee involvement, undermines the principle of employee empowerment and engagement. This can result in resistance to change, reduced morale, and missed opportunities for valuable insights from those closest to the processes, failing to leverage the full potential of the workforce as envisioned by TQM. A third incorrect approach that treats process optimization as a discrete project rather than an ongoing cycle of continuous improvement neglects the iterative nature of TQM. This leads to stagnation and a failure to adapt to evolving customer needs and technological advancements, ultimately hindering sustained quality excellence. Professionals should approach such situations by first understanding the strategic objectives and then evaluating potential process optimization strategies through the lens of TQM's core principles. This involves actively seeking customer feedback, engaging employees in problem-solving and solution development, and establishing mechanisms for ongoing monitoring and refinement. The decision-making process should prioritize approaches that foster a culture of quality, ensuring that improvements are sustainable, customer-centric, and driven by the collective effort of the organization. Question 8. The risk matrix shows a moderate correlation between the temperature of a manufacturing process and the defect rate of a critical component. A simple linear regression analysis has been performed, yielding a statistically significant p-value for the temperature variable. The regression coefficient indicates that for every 1 degree Celsius increase in temperature, the defect rate is predicted to increase by 0.5%. The certified quality engineer is tasked with recommending process adjustments. Which of the following interpretations and recommended actions best aligns with regulatory expectations for ensuring product quality and safety? Option A. focus solely on the statistical significance of the p-value, recommending a reduction in temperature as a corrective action, without further consideration of the practical implications of the 0.5% defect rate increase or the model's assumptions. Option B. Recommend further statistical analysis, such as exploring nonlinear relationships or interaction effects with other variables, without immediately proposing process adjustments, as the current model might be too simplistic to justify definitive action. Option C. Conclude that the correlation is not strong enough to warrant immediate action, as the regression coefficient suggests a relatively small increase in defect rate per degree, and focus on other identified risks in the matrix. Option D. Recommend a significant adjustment to lower the process temperature, citing the statistically significant correlation and the predicted increase in defect rate, as this directly addresses a potential driver of nonconformance and aligns with a proactive quality management approach. The correct answer is D. Recommend a significant adjustment to lower the process temperature, citing the statistically significant correlation and the predicted increase in defect rate, as this directly addresses a potential driver of nonconformance and aligns with a proactive quality management approach. Explanation: this scenario is professionally challenging because it requires a quality engineer to interpret statistical outputs in the context of regulatory compliance and potential product safety implications. The pressure to deliver a product that meets quality standards while also adhering to strict regulatory requirements necessitates a thorough understanding of regression analysis beyond mere calculation. The engineer must critically evaluate the model's applicability and interpret its findings responsibly. The correct approach involves a comprehensive interpretation of the regression analysis, considering both statistical significance and practical implications within the regulatory framework. This includes assessing the correlation coefficient to understand the strength of the relationship between variables, examining the regression coefficients for practical significance and direction of effect, and critically evaluating the model's assumptions and limitations. The regulatory framework for quality engineering, particularly in sectors with stringent oversight, e.g., medical devices, aerospace, pharmaceuticals, mandates that decisions impacting product quality and safety are based on robust, interpretable, and validated data. A responsible interpretation ensures that any identified relationships are understood in terms of their potential impact on product performance and compliance with established standards and regulations. This aligns with the ethical obligation to ensure product safety and efficacy. An incorrect approach that focuses solely on statistical significance without considering practical implications or regulatory context fails to meet professional standards. For instance, declaring a variable significant based on a p-value alone, without assessing the magnitude of its effect or its relevance to product performance and regulatory requirements, can lead to misinformed decisions. This overlooks the core principle of quality engineering, ensuring that statistical tools are used to drive meaningful improvements and maintain compliance, not just to satisfy statistical tests. Another incorrect approach would be to overemphasize correlation without understanding the nuances of linear regression, such as the potential for spurious correlations or the assumption of linearity. Relying solely on a high correlation coefficient without examining the regression coefficients, residuals, or the underlying theoretical basis for the relationship can lead to incorrect conclusions about causality or the practical impact of variables. This violates the principle of using statistical methods appropriately to understand and control processes. Furthermore, ignoring the limitations of the model, such as violations of assumptions, e.g., heteroscedasticity, non-normality of residuals, or extrapolating beyond the range of the data, represents a significant ethical and professional failure. Regulatory bodies expect that the tools used for quality assessment are applied within their valid scope, and any deviations or limitations are acknowledged and managed. The professional decision-making process for similar situations should involve 1. Understanding the regulatory context and its specific requirements related to the product or process. 2. Thoroughly analyzing the regression output, including statistical significance, effect sizes, and model diagnostics. 3. Critically evaluating the practical significance of the identified relationships in relation to product performance and safety. 4. Considering the assumptions of the regression model and assessing whether they are met. 5. Documenting the interpretation, including any limitations or uncertainties, and their implications for regulatory compliance and product quality. 6. Communicating findings clearly and responsibly to stakeholders, ensuring that decisions are data-driven and ethically sound. Question 9. The monitoring system demonstrates a consistent, albeit suboptimal, level of variation in a key process parameter. While the current output remains within acceptable specification limits, a deeper analysis of the historical data reveals a recurring pattern of minor deviations. What is the most appropriate quality engineering approach to address this situation? Option A. Initiate a root cause analysis to understand the underlying factors contributing to the observed variation and develop targeted corrective actions. Option B. Revert the process to a previously documented stable state that exhibited less variation, assuming it was optimal. Option C. Implement immediate process adjustments to eliminate the most frequent minor deviation observed in the data. Option D. Focus solely on the current specification limits, as the process is currently producing acceptable output. The correct answer is A. Initiate a root cause analysis to understand the underlying factors contributing to the observed variation and develop targeted corrective actions. Explanation. This scenario is professionally challenging because it requires a quality engineer to balance the immediate need for process improvement with the potential risks of disrupting a stable, albeit suboptimal, process. The pressure to demonstrate tangible results can lead to hasty decisions. Careful judgment is required to ensure that any changes are data-driven, validated, and do not negatively impact product quality or customer satisfaction. Adhering to the principles of continuous improvement without compromising established standards. The correct approach involves a systematic, data-driven investigation to understand the root cause of the observed variation before implementing any changes. This aligns with the core tenets of quality management, particularly process optimization, which emphasizes understanding and controlling processes. By analyzing the data to identify the specific factors contributing to the variation, the engineer can then develop targeted solutions. This methodical approach ensures that interventions are effective, efficient, and minimize the risk of unintended consequences. Regulatory frameworks for quality management, such as those outlined by ASQ, American Society for Quality, for the Certified Quality Engineer exam, emphasize a scientific and data-based approach to problem-solving and process improvement. This includes using tools like root cause analysis and statistical process control to guide decision-making, thereby ensuring compliance with quality standards and preventing deviations that could lead to non-conforming products. Implementing changes without a thorough understanding of the root cause is a significant regulatory and ethical failure. This approach risks introducing new problems or exacerbating existing ones, potentially leading to product defects, customer complaints, and non-compliance with quality standards. It bypasses the fundamental principle of evidence-based decision-making, which is a cornerstone of quality engineering and is often implicitly or explicitly required by quality management systems and regulations. Focusing solely on the most frequent deviation without considering its impact or other contributing factors is also an incomplete approach. Addressing the most common issue might seem efficient. It could overlook more critical underlying problems or lead to a solution that is not robust enough to handle the full spectrum of process variability. This can result in a superficial fix that does not achieve true process optimization and may not satisfy regulatory requirements for comprehensive process control. Another incorrect approach would be to immediately revert to a previous, known good process state without analyzing the current data. While a previous state might have been acceptable, it may not be the optimal solution, and this action ignores the opportunity to learn from the current process and potentially achieve even better results. It represents a failure to embrace continuous improvement and can be seen as a lack of proactive problem solving, potentially violating the spirit of quality management systems that encourage ongoing enhancement. The professional decision-making process for similar situations should involve 1. Data collection and analysis. Thoroughly collect and analyze all relevant data from the monitoring system. 2. Root cause identification. Employ structured problem-solving methodologies, e.g., Ishikawa diagrams, 5 whys, to identify the fundamental causes of the observed variation. 3. Solution development. Based on the root cause analysis, brainstorm and evaluate potential solutions, considering their feasibility, impact, and cost. 4. Pilot testing and validation. If feasible, pilot test proposed solutions on a small scale and validate their effectiveness before full implementation. 5. Implementation and monitoring. Implement the validated solution and continue to monitor the process to ensure sustained improvement and prevent recurrence of issues. 6. Documentation and review. Document all steps, findings, and outcomes, and periodically review the process for further optimization opportunities. This systematic approach ensures that decisions are informed, effective, and compliant with quality principles and any applicable regulations. Question 10. Upon reviewing a proposal to reduce inspection frequency for a critical component based on a statistical analysis suggesting that defects occur at a rare rate, fitting a Poisson distribution, what is the most ethically and professionally responsible course of action for a certified quality engineer? Option A. Recommend adopting the reduced inspection frequency, as the Poisson distribution statistically supports the rarity of defects, leading to cost savings. Option B. Immediately reject the proposal, as reducing inspections on critical components inherently compromises quality control regardless of statistical justification. Option C. Suggest implementing the reduced inspection frequency, but increase the sample size for the remaining inspections to compensate for the lower frequency. Option D. Conduct a comprehensive risk assessment. Validate the Poisson model's applicability with historical data and process understanding, and consider the criticality of the component before making a recommendation. Correct answer is A. Recommend adopting the reduced inspection frequency, as the Poisson distribution statistically supports the rarity of defects, leading to cost savings. Explanation. This scenario presents a professional challenge because it requires balancing the pursuit of efficiency and cost reduction with the ethical obligation to maintain product quality and customer safety. The pressure to adopt a less robust quality control method, even if statistically justifiable under certain assumptions, can lead to overlooking potential risks or failing to meet the intended quality standards. The certified quality engineer, CQE, must navigate this pressure by relying on established quality principles and regulatory requirements, rather than solely on immediate cost-benefit analyses. The correct approach involves a thorough risk assessment and adherence to established quality control methodologies, specifically considering the application of probability distributions in a way that safeguards quality. This means understanding that, while a Poisson distribution might model rare events, its application in quality control must be validated against actual process performance and potential consequences of defects. The CQE's responsibility is to ensure that any chosen control method, regardless of its statistical basis, effectively monitors and maintains product quality within acceptable limits, aligning with the principles of quality management systems and potentially industry-specific regulations that mandate certain levels of quality assurance. The ethical imperative is to prioritize product integrity and customer well-being over short-term cost savings. An incorrect approach would be to immediately adopt the proposed change based solely on the statistical model without further investigation or validation. This fails to acknowledge that statistical models are simplifications of reality and may not capture all relevant factors or potential failure modes. Relying solely on the Poisson distribution to justify a less frequent inspection schedule, without considering the criticality of the product, the potential impact of a defect, or the historical variability of the process, is a significant ethical and professional failure. It bypasses the due diligence required to ensure quality and could lead to the release of non-conforming products, violating quality standards and potentially regulatory requirements. Another incorrect approach would be to dismiss the proposal outright without proper consideration. While caution is warranted, a complete rejection without understanding the statistical rationale or exploring potential valid applications of probability distributions in quality control is also professionally unsound. A CQE should be able to critically evaluate such proposals, understand the underlying statistical principles, and determine their applicability and limitations within the specific quality control context. The professional decision-making process for similar situations should involve 1. Understanding the proposed change and its underlying statistical rationale. 2. Evaluating the proposed statistical model, e.g., Poisson, in the context of the specific product, process, and potential risks. 3. Conducting a thorough risk assessment to understand the consequences of potential defects. 4. Verifying the applicability and limitations of the chosen statistical distribution with actual process data and historical performance. 5. Considering relevant industry standards, regulatory requirements, and customer expectations. 6. recommending a quality control strategy that balances efficiency with robust quality assurance, prioritizing product safety and customer satisfaction. 7. Documenting the decision-making process and the rationale for the chosen approach. Question 11. Stakeholder feedback indicates significant skepticism and a lack of understanding regarding the proposed organization-wide implementation of Six Sigma, with many employees questioning its relevance to their daily tasks and expressing concerns about increased workload. What is the most effective approach to address this challenge and ensure successful Six Sigma adoption? Option A. Focus exclusively on training employees on advanced Six Sigma statistical tools and techniques, assuming understanding will follow tool mastery. Option B. Mandate the immediate adoption of Six Sigma across all departments, providing generic training materials to all employees. Option C. Initiate a pilot Six Sigma project in a specific department to demonstrate tangible benefits and gather lessons learned before a broader rollout, coupled with targeted communication and training. Option D. Proceed with the original organization-wide implementation plan as designed, dismissing the feedback as typical resistance to change. The correct answer is C. Initiate a pilot Six Sigma project in a specific department to demonstrate tangible benefits and gather lessons learned before a broader rollout, coupled with targeted communication and training. Explanation. This scenario presents a common challenge in Six Sigma implementation: resistance to change, and a lack of understanding regarding the methodology's benefits and requirements. Professional challenge lies in effectively communicating the value of Six Sigma, addressing concerns, and securing buy-in from all levels of the organization, especially when faced with skepticism. Careful judgment is required to tailor the approach to the specific organizational culture and stakeholder needs, ensuring that the implementation is perceived as a collaborative effort rather than an imposed mandate. The correct approach involves a structured, phased rollout of Six Sigma, beginning with a pilot project. This strategy allows for demonstrating tangible results and building confidence before a broader deployment. It aligns with principles of change management and risk mitigation, common in quality management frameworks. By starting small, the team can identify and address potential roadblocks in a controlled environment, gather lessons learned, and refine the implementation plan. This phased approach also allows for targeted training and support for those directly involved in the pilot, fostering early champions for the methodology. This aligns with the ASQ Certified Quality Engineer body of knowledge, which emphasizes practical application and continuous improvement through iterative learning. An incorrect approach would be to immediately mandate Six Sigma across the entire organization without prior demonstration or stakeholder engagement. This can lead to widespread resistance, a perception of top-down imposition, and a failure to address specific departmental needs or concerns. Such a broad, unproven rollout risks alienating employees and undermining the credibility of the Six Sigma initiative from the outset, potentially violating ethical considerations of fair and transparent implementation. Another incorrect approach is to focus solely on the technical tools of Six Sigma, e.g., statistical analysis, without addressing the human element of change management. While tools are critical, their effectiveness is diminished if the underlying organizational culture is not prepared or if employees do not understand the why behind their use. This oversight can lead to superficial adoption, where tools are used without true understanding or commitment, failing to achieve the desired process improvements and potentially leading to wasted resources. This neglects the ethical responsibility to ensure that quality initiatives are implemented in a way that respects and empowers the workforce. Finally, an incorrect approach would be to dismiss stakeholder feedback as mere resistance and proceed with the original plan without adaptation. This demonstrates a lack of respect for the concerns of those who will be directly impacted by the changes. It can create an adversarial environment, hindering collaboration and ultimately jeopardizing the success of the Six Sigma implementation. Ethical quality management requires active listening and responsiveness to stakeholder input to ensure that initiatives are well received and sustainable. The professional decision-making process for similar situations involves a thorough assessment of the organizational landscape, including culture, existing processes, and stakeholder perspectives. It requires a strategic approach to change management, emphasizing communication, education, and the demonstration of value. A pilot program, followed by iterative expansion based on demonstrated success and feedback, is often the most effective and ethically sound method for introducing new methodologies like Six Sigma. Question 12. The efficiency study reveals significant opportunities to reduce operational costs by streamlining certain quality assurance processes. Which of the following approaches best aligns with the principles of quality management and regulatory compliance for a certified quality engineer? Option A. Conduct a comprehensive root cause analysis of the identified inefficiencies. Identify process improvements that maintain or enhance product quality and customer satisfaction, and implement validated solutions with appropriate control measures. Option B. Immediately eliminate redundant quality control checkpoints identified in the study to achieve rapid cost savings, assuming that the overall quality of the final product will not be significantly affected. Option C. Outsource a significant portion of the quality inspection activities to a third-party provider that offers substantially lower rates, without a thorough vendor assessment or ongoing performance monitoring. Option D. Implement a new, highly automated inspection technology to replace manual checks, based on vendor claims of increased speed and reduced labor costs, without conducting extensive pilot testing or validation. The correct answer is A. Conduct a comprehensive root cause analysis of the identified inefficiencies. Identify process improvements that maintain or enhance product quality and customer satisfaction, and implement validated solutions with appropriate control measures. Explanation. This scenario is professionally challenging because it requires balancing the drive for efficiency and cost reduction with the fundamental principles of quality management and regulatory compliance. A certified quality engineer must navigate potential conflicts between immediate financial gains and long-term product integrity, customer satisfaction, and adherence to established quality standards. The pressure to demonstrate cost savings can sometimes lead to shortcuts that compromise quality, making objective evaluation and ethical decision-making paramount. Correct approach involves a thorough root cause analysis of the identified inefficiencies and the subsequent implementation of solutions that address the underlying issues without negatively impacting product quality or customer experience. This aligns with the core tenets of quality management systems, such as ISO 9001, which emphasize continuous improvement, customer focus, and process-based approaches. Specifically, a robust Six Sigma DMAIC, define, measure, analyze, improve, control methodology would be employed. The analyze phase is critical for understanding the true drivers of inefficiency, and the improve phase focuses on implementing solutions that are validated to maintain or enhance quality. Regulatory compliance, depending on the specific industry, e.g., FDA for medical devices, FAA for aerospace, mandates that quality standards are not compromised, and any process changes must be documented and validated to ensure continued adherence to safety and performance requirements. Ethical considerations demand that the pursuit of efficiency does not lead to the production of substandard products or services that could harm consumers or damage the company's reputation. An incorrect approach that focuses solely on immediate cost reduction by eliminating quality control checkpoints without a thorough understanding of their impact is professionally unacceptable. This disregards the fundamental purpose of these checkpoints, which is to prevent defects and ensure product conformity. Such an action would likely violate quality management system requirements and could lead to increased customer complaints, product recalls, and significant regulatory penalties. Another incorrect approach that involves implementing a new, unproven technology to achieve efficiency without adequate testing and validation is also professionally unsound. This bypasses the critical improve and control phases of Six Sigma and the validation requirements of most regulatory frameworks. The risk of introducing new defects or systemic failures is high, potentially leading to greater costs in the long run due to rework, scrap, and customer dissatisfaction. A third incorrect approach that involves outsourcing a critical quality assurance function to a vendor with lower quality standards to reduce costs. Without a rigorous vendor qualification process and ongoing performance monitoring, is ethically and professionally flawed. This abdicates responsibility for quality and can lead to a cascade of quality issues that are difficult to trace and rectify, ultimately harming the company's reputation and potentially violating contractual obligations and regulatory requirements. Professionals should employ a structured decision-making process that begins with clearly defining the problem and its impact. This involves gathering data, analyzing root causes, and identifying potential solutions. Each proposed solution must then be evaluated against established quality standards, regulatory requirements, and ethical considerations. A risk assessment should be conducted for each potential solution, considering its impact on product quality, customer satisfaction, cost, and compliance. The chosen solution should be piloted, validated, and then implemented with robust control measures to ensure sustained effectiveness. Continuous monitoring and feedback loops are essential for ongoing improvement and to identify any unintended consequences. Question 13. Examination of the data shows that a new quality control procedure, designed to significantly reduce product defects, requires substantial changes to the daily workflows of the production floor staff. Initial feedback indicates apprehension and a reluctance to adopt the new steps, with some employees expressing concerns about increased workload and the complexity of the new documentation. As the certified quality engineer responsible for this implementation, which of the following strategies best addresses this situation to ensure successful adoption and foster a culture of continuous improvement? Option A. Mandate immediate adherence to the new procedure through a directive from senior management, emphasizing the consequences of noncompliance. Option B. Implement a comprehensive communication plan detailing the benefits of the new procedure. Provide hands-on training sessions tailored to different roles and establish feedback channels for ongoing adjustments. Option C. Delegate the entire implementation and training responsibility to the immediate supervisors of the production floor, with minimal direct involvement from the quality engineering department. Option D. Offer a one-time bonus to all production staff upon successful completion of the initial implementation phase of the new procedure. The correct answer is B. Implement a comprehensive communication plan detailing the benefits of the new procedure, provide hands-on training sessions tailored to different roles, and establish feedback channels for ongoing adjustments. Explanation. This scenario presents a common challenge in quality engineering, implementing a new process that requires significant behavioral and procedural shifts across an organization. The professional challenge lies in balancing the need for efficient and effective change with the inherent human resistance to altering established routines and the potential for disruption to ongoing operations. A quality engineer must not only understand the technical merits of the new process, but also possess the skills to navigate the human element of change. Careful judgment is required to select strategies that promote buy-in, mitigate resistance, and ensure the long-term sustainability of the improved process, all while adhering to relevant quality standards and ethical considerations. The correct approach involves a multifaceted strategy that prioritizes communication, training, and stakeholder involvement. This approach acknowledges that change is not solely a technical implementation, but a socio-technical one. By clearly articulating the rationale behind the change, providing comprehensive training, and actively involving affected personnel in the implementation, resistance is minimized and a sense of ownership is fostered. This aligns with the principles of quality management systems, such as those outlined in ISO 9001, which emphasize leadership commitment, engagement of people, and a process approach. Ethically, this approach respects the individuals affected by the change by valuing their input and providing them with the necessary resources to adapt. An incorrect approach that focuses solely on top-down mandates without adequate communication or training fails to address the root causes of resistance. This can lead to superficial compliance, increased errors, and a breakdown in morale, ultimately undermining the intended quality improvements. Such an approach may also violate ethical principles by disregarding the impact on employees and failing to provide them with the support needed to perform their duties effectively under the new system. Another incorrect approach that relies on incentivizing compliance without addressing underlying concerns or providing clear understanding can create a transactional relationship with change. While short-term adherence might be achieved, it does not foster a genuine culture of continuous improvement. This can lead to a situation where employees only comply when incentives are present, and the long-term adoption of the new process is jeopardized. This approach lacks the ethical consideration of building sustainable positive change and can be seen as manipulative. A third incorrect approach that involves isolating the change initiative to a small team without broader organizational engagement risks creating a disconnect between the implementers and the rest of the workforce. This can result in a lack of understanding, skepticism, and resistance from those not directly involved, hindering widespread adoption and integration of the new process. Ethically, this approach fails to ensure equitable treatment and opportunity for all employees to understand and contribute to organizational improvements. A professional decision-making process for similar situations should involve a thorough assessment of the proposed changes' impact on people, processes, and systems. It requires proactive identification of potential resistance points and the development of strategies to address them. This includes open and honest communication, robust training programs, and mechanisms for feedback and continuous improvement. Quality engineers must act as change facilitators, leveraging their understanding of quality principles to guide the organization through transitions in a manner that is both effective and ethically sound, ensuring that the pursuit of quality does not come at the expense of employee well-being or organizational trust. Question 14. Assessment of the reliability of data collection methods for a critical process parameter is paramount before initiating detailed process mapping and baseline performance measurement. Which of the following actions is the most appropriate initial step to ensure the integrity of the data that will be used for subsequent analysis and decision-making? Option A. Assume the measurement system is adequate due to its long-standing use within the organization. Option B. Proceed directly with detailed process mapping and collect baseline performance data using existing measurement tools. Option C. Rely on historical data collected over the past 5 years, assuming the measurement system has remained consistent. Option D. Conduct a measurement system analysis, MSA, study to evaluate the variation and accuracy of the measurement system. Correct answer is D. Conduct a measurement system analysis, MSA, study to evaluate the variation and accuracy of the measurement system. Explanation. Scenario analysis. This scenario presents a common challenge in the measure phase of quality improvement projects, ensuring the reliability and accuracy of the data collected to understand a process. The professional challenge lies in selecting the most appropriate method to validate the measurement system, as flawed data can lead to incorrect conclusions, wasted resources, and ultimately, ineffective process improvements. The certified quality engineer must exercise careful judgment to avoid making decisions based on unreliable information. Correct approach analysis. The correct approach involves conducting a measurement system analysis, MSA study. This is the standard and ethically sound practice for validating measurement systems. An MSA systematically evaluates the variation introduced by the measurement system itself, distinguishing it from the actual process variation. This aligns with the fundamental principles of quality engineering, which emphasize data integrity and the need for reliable inputs for analysis and decision-making. Regulatory frameworks and industry best practices, such as those often referenced in quality engineering certification, mandate that the tools and methods used to collect data must be proven to be capable and accurate before drawing conclusions about process performance. Failing to validate the measurement system is a direct contravention of this principle, as it risks basing critical decisions on potentially misleading data. Incorrect approaches analysis. Proceeding with process mapping and baseline performance measurement without first validating the measurement system is professionally unacceptable. This approach fails to acknowledge the potential for measurement error to distort the perceived performance of the process. If the measurement system is not capable, the collected data will not accurately reflect the true state of the process, rendering the process map and baseline performance metrics unreliable. This can lead to misidentification of root causes, the implementation of ineffective solutions, and a failure to achieve desired quality objectives, which is a breach of professional responsibility to ensure effective quality management. Relying solely on historical data without assessing the current measurement system's validity is also an incorrect approach. Historical data may have been collected using a measurement system that is no longer in use or has degraded over time. Without an MSA, there is no assurance that this historical data is representative of current conditions or that the measurement system used to collect it was adequate. This introduces significant risk of drawing incorrect conclusions about process trends and performance. Assuming the measurement system is adequate because it has been used for a long time is a dangerous assumption and a failure of due diligence. Longevity of use does not equate to inherent accuracy or capability. Measurement systems can drift, be subject to environmental changes, or have inherent biases that only become apparent through systematic analysis. This approach neglects the proactive risk management expected of a certified quality engineer. Professional reasoning. Professionals should approach the measure phase with a risk-based mindset, prioritizing the validation of data integrity. The decision-making process should involve 1. identifying critical to quality, CTQ characteristics and the measurement methods used to capture them. 2. Assessing the potential impact of measurement error on project objectives. 3. Prioritizing the validation of measurement systems for critical characteristics through appropriate MSA techniques. 4. Only after the measurement system is deemed capable, proceed with data collection, process mapping, and baseline performance measurement. 5. Continuously monitor measurement system performance throughout the project lifecycle. Question 15. Which approach would be most effective for a certified quality engineer to communicate the results of a complex statistical analysis of product defect rates to a non-technical executive team, focusing on actionable insights and business implications? Option A. Providing a high-level summary that translates the statistical findings into key business metrics, e.g., cost of poor quality, customer impact, highlights critical trends and risks, and proposes strategic recommendations for improvement. Option B. Focusing only on the positive quality trends observed, omitting any data that might indicate potential problems or areas needing further attention. Option C. Delivering a presentation that delves deeply into the specific methodologies and algorithms used in the statistical analysis, without explicitly linking them to business outcomes. Option D. Presenting a detailed report filled with statistical formulas, control charts, and technical terminology, assuming the executives can interpret the raw data. The correct answer is D. Presenting a detailed report filled with statistical formulas, control charts, and technical terminology, assuming the executives can interpret the raw data. Explanation. Scenario analysis. This scenario presents a common challenge for quality engineers, communicating complex technical quality data to a non-technical executive team. The challenge lies in translating detailed statistical findings and potential risks into actionable business insights, without oversimplifying to the point of losing critical information or overwhelming the audience with jargon. The executive team's decision-making capacity is directly impacted by the clarity and accuracy of the information presented, making effective communication paramount for strategic quality initiatives and resource allocation. Correct approach analysis. The correct approach involves tailoring the communication to the audience by focusing on the business implications of the quality data. This means translating technical metrics into terms that resonate with executive priorities, such as cost of poor quality, customer satisfaction, market competitiveness, and potential regulatory compliance issues. The certified quality engineer, CQE, must use clear, concise language, supported by impactful visuals, charts, graphs that highlight trends and key takeaways. The goal is to provide a high-level overview of the quality status, identify critical areas requiring attention, and propose strategic recommendations, rather than detailing the statistical methodologies used. This aligns with the ethical responsibility of a CQE to ensure that quality information is understood and acted upon by all relevant stakeholders, fostering a culture of quality throughout the organization. While specific U.S. regulations for quality engineering communication aren't explicitly codified in a single document, the principles of transparency, accuracy, and stakeholder engagement are fundamental to professional practice and are often implicitly expected by regulatory bodies overseeing product quality and safety, such as the FDA or EPA, in their oversight of quality management systems. Incorrect approaches analysis. Presenting raw, uninterpreted statistical data with technical jargon fails to meet the needs of the executive audience. This approach neglects the fundamental principle of effective communication, which requires understanding and adapting to the audience's level of technical expertise. It risks confusing or disengaging the executives, leading to misinformed decisions or a lack of necessary action, which could have downstream consequences for product quality and organizational reputation. Providing only positive quality metrics without acknowledging potential risks or areas for improvement is a form of incomplete and potentially misleading communication. While executives appreciate good news, a responsible CQE must also highlight challenges and opportunities for enhancement. Omitting critical information, even if it's negative, can lead to a false sense of security and prevent proactive problem-solving, which is a failure in professional duty to provide a comprehensive quality assessment. Focusing solely on the technical details of the quality control processes without explaining their impact on business outcomes is another failure. Executives are primarily concerned with the so what, how quality affects the bottom line, customer loyalty, and strategic goals. A purely technical explanation, however accurate, will likely be perceived as irrelevant and will not facilitate informed decision-making. This approach misses the opportunity to advocate for quality initiatives and secure necessary resources. Professional reasoning. Professionals should adopt a stakeholder-centric communication strategy. This involves first identifying the audience and their information needs, technical understanding, and decision-making authority. Then, the quality engineer must translate complex technical information into clear, concise, and relevant business terms, using appropriate visuals and avoiding jargon. The communication should be balanced, presenting both successes and challenges, and always offering actionable recommendations. This approach ensures that quality information is not just delivered, but understood and utilized effectively to drive organizational improvement and uphold professional integrity. Question 16. Implementation of a new manufacturing process requires the creation of detailed procedures, work instructions, and associated forms. Which of the following best practices for quality system documentation management ensures regulatory compliance and operational efficiency? Option A. Store all draft and final versions of documents in a shared network folder accessible to all employees without a formal version control mechanism. Option B. Rely on informal communication and email to inform relevant personnel about changes to procedures and forms as they are developed. Option C. Establish a formal document control system with defined processes for creation, review, approval, distribution, revision, and retention, ensuring only current approved versions are accessible. Option D. Focus on rapidly generating new documents for the new process, without a structured review and approval workflow before implementation. The correct answer is C. Establish a formal document control system with defined processes for creation, review, approval, distribution, revision, and retention, ensuring only current approved versions are accessible. Explanation. This scenario presents a common challenge in quality management. Ensuring that documentation accurately reflects current processes and is accessible to those who need it, while also maintaining control over revisions. The professional challenge lies in balancing the need for efficient operations with the imperative of regulatory compliance and the integrity of the quality system. A failure in documentation management can lead to nonconformances, product defects, and regulatory penalties. The correct approach involves establishing a robust document control system that includes clear procedures for creation, review, approval, distribution, revision, and retention of all quality system documents. The system ensures that only current, approved versions are in use, and that changes are managed systematically. This aligns with the fundamental principles of quality management systems, such as those outlined in ISO 9001, which mandate effective document control to ensure consistency and traceability. Specifically, regulatory frameworks for quality engineers often require documented procedures for all processes that affect product quality, including the management of these documents themselves. This systematic approach prevents the use of outdated or incorrect information, thereby safeguarding product quality and compliance. An approach that relies on informal communication for updates, without a formal revision process and controlled distribution, fails to establish a verifiable record of document changes and can lead to the widespread use of incorrect procedures. This violates the principle of documented information and can result in significant quality issues and noncompliance with regulatory requirements for controlled documentation. Another incorrect approach, which involves storing all documents in a single, unmanaged folder accessible to everyone, bypasses essential controls. This lacks version control, making it impossible to determine the current approved version, and creates a high risk of accidental or intentional modification of critical documents. It also fails to provide an audit trail of who accessed or modified documents, which is often a regulatory requirement. Finally, an approach that focuses solely on creating new documents without a clear plan for their review, approval, and integration into the existing system is incomplete. This can lead to a proliferation of unverified or conflicting documentation, undermining the integrity and effectiveness of the quality system. Regulatory bodies expect a comprehensive and controlled documentation lifecycle. Professionals should approach documentation management by first understanding the specific regulatory requirements applicable to their industry and jurisdiction. They should then design and implement a formal document control procedure that covers the entire lifecycle of each document, from creation to obsolescence. This procedure should be clearly documented, communicated, and consistently followed. Regular audits of the documentation system are crucial to ensure its ongoing effectiveness and compliance. Question 17. The performance metrics show a noticeable upward trend after the implementation of a new process control procedure. As a certified quality engineer, which of the following approaches would be the most appropriate for validating this observed improvement and making a data-driven recommendation for wider adoption? Option A. Conduct a hypothesis test, e.g., t-test or chi-square test, depending on data type, to determine if the observed improvement is statistically significant, and supplement this with confidence intervals to estimate the range of the true effect. Option B. Calculate the average improvement in the performance metric and present this value as evidence of the procedure's success. Option C. Visually inspect the trend line on a control chart and conclude that the improvement is sufficient for wider implementation. Option D. Select a statistical test at random and apply it to the data, regardless of the data's characteristics or the test's assumptions. The correct answer is B. Calculate the average improvement in the performance metric and present this value as evidence of the procedure's success. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a quality engineer to move beyond simply observing data to actively interpreting it and making recommendations based on statistical inference. The challenge lies in selecting the appropriate inferential statistical tool to validate a perceived improvement and ensuring that the chosen method aligns with the principles of quality management and any applicable regulatory standards for data integrity and decision-making. Misinterpreting the data or using an inappropriate statistical test can lead to incorrect conclusions, wasted resources, or even regulatory noncompliance if the decisions impact product quality or safety. Correct approach analysis. The correct approach involves using inferential statistics, specifically hypothesis testing, to determine if the observed improvement in performance metrics is statistically significant or likely due to random variation. This aligns with best practices in quality engineering, which emphasize data-driven decision-making and the validation of process changes. For instance, if the performance metric is a continuous variable and the sample size is sufficient, a t-test or z-test, depending on whether the population standard deviation is known, would be appropriate to compare the means of the pre- and post-intervention data. If the metric is categorical, a chi-square test might be used to assess independence between categories before and after the intervention. Confidence intervals provide a range of plausible values for the true population parameter, further supporting the assessment of the intervention's impact. This rigorous statistical approach ensures that conclusions are based on evidence and not just anecdotal observation, which is crucial for maintaining product quality and meeting regulatory expectations for process control and validation. Incorrect approaches analysis. One incorrect approach would be to solely rely on descriptive statistics, such as calculating the average improvement, without performing hypothesis testing. This fails to account for the inherent variability in data and can lead to overstating the impact of the intervention. It lacks the rigor required to confidently assert that the observed change is real and not a result of random chance, which is a fundamental failure in quality engineering's mandate for objective evidence. Another incorrect approach would be to arbitrarily select a statistical test without considering the nature of the data, continuous vs. categorical, or the assumptions of the test. For example, using a t-test for categorical data or a chi-square test for normally distributed continuous data would violate the underlying statistical principles, rendering the results invalid and leading to flawed conclusions. This demonstrates a lack of understanding of inferential statistics and a failure to apply them correctly, which is a significant ethical and professional lapse in a quality engineering context. A third incorrect approach would be to ignore the statistical significance and proceed with implementing changes based on a perceived trend. This bypasses the critical step of validation, which is essential for ensuring that improvements are robust and sustainable. It also disregards the potential for type I or type Roman II errors inherent in statistical inference, leading to potentially costly and ineffective decisions. Professional reasoning. Professionals should adopt a systematic approach to inferential statistics. First, clearly define the problem and the hypothesis to be tested. Second, understand the nature of the data and select the most appropriate statistical test based on its characteristics and assumptions. Third, conduct the test and interpret the results, considering statistical significance and practical significance. Fourth, use confidence intervals to provide a range of plausible values for the population parameter. Finally, communicate the findings clearly and transparently, including any limitations of the analysis, to support informed decision-making and ensure adherence to quality standards and regulatory requirements. Question 18. During the evaluation of a critical component's dimensional accuracy for a new aerospace contract, a certified quality engineer, CQE, conducts a gauge repeatability and reproducibility gauge R&R study on the primary measurement system. The initial results indicate a significant level of variation attributed to the measurement system, exceeding acceptable industry thresholds. The customer, eager to receive the first shipment, is pressing for immediate acceptance of the measurement system to expedite production. The CQE is aware that addressing the identified measurement system issues will cause a delay in production and potentially impact the delivery schedule. Which of the following actions represents the most ethically and professionally sound approach for the CQE? Option A. Adjust the parameters of the gauge R&R study or selectively exclude certain data points to achieve a result that meets the customer's implicit or explicit acceptance criteria. Option B. Recommend using a different, less precise measurement system that has historically shown better gauge R&R results, even though it is not the primary system specified for this critical dimension, to meet the customer's timeline. Option C. Immediately halt production and inform the customer and internal stakeholders that the measurement system is not capable and requires further investigation and corrective actions before any product can be accepted, even if it causes significant delays. Option D. Proceed with accepting the measurement system for production, documenting the gauge R&R findings but deeming them acceptable for the immediate customer need, and planning to address the variation in a future improvement project. The correct answer is D. Proceed with accepting the measurement system for production, documenting the gauge R&R findings but deeming them acceptable for the immediate customer need, and planning to address the variation in a future improvement project. Explanation. This scenario presents a professional challenge because it involves a conflict between achieving a desired outcome, meeting a customer's specification, and maintaining the integrity of quality data. The Certified Quality Engineer, CQE, is tasked with ensuring the accuracy and reliability of measurement systems, which is foundational to all quality decisions. The pressure to meet customer requirements can tempt an engineer to overlook or downplay potential issues with the measurement system, creating an ethical dilemma. Careful judgment is required to balance customer satisfaction with the ethical obligation to report accurate data and ensure robust processes. The correct approach involves conducting a thorough gauge repeatability and reproducibility gauge R&R study as per established quality engineering principles and relevant industry standards, e.g., AEG MSA manual, which is a de facto standard in many U.S. regulated industries. This study objectively assesses the variation introduced by the measurement system itself. If the gauge R&R indicates unacceptable variation, the engineer must then investigate the root causes of this variation, which could include issues with the gauge, the operator, or the measurement method. Addressing these root causes before accepting the measurement system is crucial for ensuring that subsequent product acceptance decisions are based on reliable data. This upholds the ethical responsibility to provide accurate information and the professional obligation to implement effective quality control. An incorrect approach would be to proceed with accepting the measurement system without addressing the identified issues, especially if the gauge R&R results are poor. This bypasses the fundamental purpose of MSA, which is to ensure the measurement system is capable of distinguishing between acceptable and unacceptable product. Ethically, this is a failure to uphold professional integrity and could lead to the acceptance of non-conforming product, potentially causing customer dissatisfaction, product recalls, and damage to the company's reputation. It also violates the principle of data-driven decision-making. Another incorrect approach would be to manipulate the data or the study parameters to achieve a favorable gauge R&R result. This is a direct ethical breach, as it involves falsifying or misrepresenting data. Such actions undermine the entire quality system and erode trust. It is a violation of professional conduct and can have severe legal and financial repercussions. A third incorrect approach would be to dismiss the gauge R&R findings as insignificant without proper investigation, especially if the customer is pressuring for immediate acceptance. While some variation is inherent in any measurement system, A statistically significant level of variation requires investigation and mitigation. Ignoring these findings, even with good intentions to satisfy the customer, is a failure to apply sound engineering principles and can lead to long-term quality problems. The professional decision-making process for similar situations should involve a systematic approach. 1. Understand the requirements and the potential impact of measurement error. 2. Adhere strictly to established methodologies for MSA such as the Gauge R&R study. 3. Objectively analyze the results of the MSA. 4. If issues are identified, prioritize root cause analysis and corrective actions. 5. Communicate findings and propose solutions transparently to stakeholders, including management and the customer, explaining the implications of measurement system performance on product quality. 6. Resist pressure to compromise data integrity or quality standards. 7. Document all steps taken, including the MSA results, root cause analysis, and corrective actions. Question 19. Benchmark analysis indicates that a manufacturing company is facing significant pressure to reduce operational costs while simultaneously improving product defect rates. The quality manager, a certified quality engineer, is tasked with leading a cross-functional team to implement new quality control measures. The manager is considering different leadership styles to achieve these dual objectives. Which leadership style is most likely to foster a sustainable culture of quality improvement and ethical compliance in this challenging environment? Option A. Transactional leadership, emphasizing clear performance metrics, rewards for meeting defect reduction targets, and penalties for non-compliance. Option B. Laissez-faire leadership, allowing the team complete freedom to manage their own quality processes and problem-solving approaches. Option C. Transformational leadership, focusing on inspiring the team with a vision of superior quality and empowering them to innovate solutions. Option D. Servant leadership, prioritizing the team's needs and well-being and facilitating their self-directed efforts towards quality goals. Correct answer is C. Transformational leadership, focusing on inspiring the team with a vision of superior quality and empowering them to innovate solutions. Explanation. This scenario presents a professional challenge because it requires balancing the immediate need for cost reduction with the long-term imperative of maintaining and improving product quality, which is directly tied to customer satisfaction and regulatory compliance. The chosen leadership style significantly influences how effectively quality initiatives are implemented and sustained. A leader must ethically consider the impact of their decisions on all stakeholders, including employees, customers, and the organization's reputation, all within the framework of the certified quality engineer's responsibilities. The transformational leadership approach is the most appropriate in this situation. This style focuses on inspiring and motivating employees to achieve higher levels of performance and commitment, fostering a shared vision for quality improvement. It encourages innovation and empowers individuals to take ownership of quality processes, leading to more sustainable and effective quality initiatives. This aligns with the ethical responsibility of a certified quality engineer to promote a culture of quality and continuous improvement, which often requires buy-in and engagement beyond mere transactional exchanges. Adopting a purely transactional leadership style would be ethically problematic. While it might offer short-term gains through clear reward and punishment systems, it risks demotivating employees by focusing solely on immediate task completion and compliance. This can stifle creativity and discourage proactive problem-solving, hindering the development of a robust quality culture. It fails to address the underlying systemic issues that might be contributing to quality concerns and could lead to a superficial adherence to standards rather than a genuine commitment to excellence. A servant leadership approach, while noble in its intent to serve others, might not be the most effective primary strategy for driving immediate, impactful quality initiatives in a cost-cutting environment. While it fosters trust and employee well-being, its focus on empowerment and development might be slower to yield the decisive actions needed to address urgent quality challenges and cost pressures. It could inadvertently lead to a lack of clear direction or accountability if not carefully managed alongside other leadership elements. The professional reasoning process for such a situation involves a thorough assessment of the current organizational climate, the specific quality challenges, and the strategic objectives. A certified quality engineer must consider which leadership style will best foster the necessary engagement, innovation, and accountability to achieve both short-term cost efficiencies and long-term quality excellence. This requires ethical deliberation on the impact of leadership choices on employee morale, customer trust, and regulatory adherence, ultimately selecting the approach that best supports a sustainable culture of quality. Question 20. Performance analysis shows a consistent trend of customer complaints related to product defects originating from the manufacturing department. The quality manager is tasked with planning an internal audit of this department's quality management system. The quality manager directly oversees the manufacturing department's operations and has a close working relationship with its director. Considering the need for an objective and effective audit, which of the following approaches to assigning the internal auditor would best uphold the principles of quality auditing and professional ethics? Option A. The quality manager assigns an auditor from the quality assurance team who has no direct reporting relationship to the manufacturing department's director. Option B. The quality manager decides to conduct the audit themselves due to their comprehensive understanding of the department's processes. Option C. The quality manager assigns an auditor who reports directly to the manufacturing department's director to conduct the audit. Option D. The quality manager postpones the audit indefinitely, citing ongoing production pressures and a lack of readily available audit personnel. The correct answer is A. The quality manager assigns an auditor from the quality assurance team who has no direct reporting relationship to the manufacturing department's director. Explanation. This scenario is professionally challenging because it requires balancing the need for thorough internal quality auditing with the potential for perceived bias or conflict of interest when an auditor has a direct reporting relationship to the auditee's management. The certified quality engineer, CQE, must navigate these dynamics to ensure the audit's integrity and effectiveness, adhering strictly to the principles of impartiality and objectivity inherent in quality auditing standards. The correct approach involves the quality manager assigning an auditor who is independent of the department being audited. This ensures objectivity and impartiality, which are fundamental tenets of effective quality auditing. Regulatory frameworks and professional ethical guidelines for quality professionals, such as those often referenced in CQE certifications, which typically align with international standards like ISO 19011 for auditing management systems, emphasize the need for auditors to be free from conflicts of interest and to maintain an objective approach. This independence allows for an unbiased assessment of the department's quality management system, leading to more credible findings and actionable recommendations. An approach where the quality manager assigns an auditor who reports directly to the auditee's management is professionally unacceptable. This creates a direct conflict of interest and compromises the auditor's independence. The auditor may feel undue pressure to overlook nonconformities or to soften findings to maintain a positive relationship with their direct superior, who is also the head of the department being audited. This undermines the credibility of the audit process and the reliability of its outcomes, violating the ethical obligation of an auditor to be impartial and to report findings truthfully and accurately. Another unacceptable approach is for the quality manager to conduct the audit themselves, given their direct oversight of the auditee's department. While the quality manager has a vested interest in the department's performance, their direct managerial role introduces a significant conflict of interest. They are responsible for the department's overall success, which can cloud their judgment when identifying systemic issues or holding the department accountable for nonconformities. This violates the principle of auditor independence and can lead to a compromised audit. Finally, an approach where the audit is postponed indefinitely due to perceived scheduling conflicts, without a clear plan for rescheduling or addressing the immediate quality concerns, is also professionally deficient. While scheduling can be a practical challenge, it should not be used as a reason to avoid necessary quality assurance activities. The professional responsibility of a CQE includes ensuring that audits are conducted in a timely manner to identify and address potential quality issues, thereby preventing larger problems and ensuring continuous improvement. The professional decision-making process for similar situations should involve 1. Identifying potential conflicts of interest or biases. 2. Consulting relevant quality auditing standards and ethical guidelines. 3. Prioritizing auditor independence and objectivity. 4. Developing a clear audit plan that addresses potential challenges, including resource allocation and auditor assignment. 5. Communicating transparently with all stakeholders about the audit process and its objectives.